Yeah, so myself Ghulam Murtaza. I'm master student at NCHU. So today I'm going to present this presentation to Professor Dr. Hong Wanman, who was the instructor of this course, Condensed Matter Physics. So without any further ado, I just would like to jump to the main topic. Uh, But before this, I just would like to talk about the crystal structure, just the overview of crystal structure, because the crystal structure is very important and it's a play key roles because without knowing about the crystal structure, we are not able to know the actual thing behind any kind of material. So that's why to knowing the crystal structure, it's a very important to know about the phenomena which are going to be happen inside the any kind of material. So the basic question that what is crystal structure? So crystal structure is a description of the ordered arrangement of atoms, ions, or molecules in a crystalline material. So other structure occurs from the intrinsic nature of constituent particles to form symmetric pattern. That's the repeat along the principal's direction of three-dimensional space in matter. So here it was something about the crystal structure. So here we gonna see the example of a crystal structure. So studying here are the various form of condensed matter, and you know many of them already. The reason why we are all in the same slides because it is the same because it's the difference between the amount of ordering or the about the symmetry that these different classes of materials possess, and we go to be focused on the crystal structure themselves. So just crystal without molecular crystal or quasi crystal or liquid crystal, just crystal is the periodic arrangement of the atoms, so which can be also characterized by a lattice. For example, this is the salt crystal, and these are quartz crystal, and these are the real picture of them. And here we can also see the crystal structure of these structures, which manifests even on a macroscope scale. So and because this these are the various planes that we can also hear that the clay plays, so we can try to grow a crystal and it will form these planes that could be natural where the atoms terminate in a nice way. uh, for example, this is the crystal break crystal. It will turn to break along spatial planes. So crystal structure sometimes see it on the macroscopic scale in these big crystal. So also there are some things with less order. For example, so I just wait a moment. This so so here are some liquid examples, and I just in the direction unless some special liquid, some molecules rotate free and move around. So in the principle, if we are in the liquid at some point and we are here in a liquid hedge point, and the environment is not, I think, ordered, but the environment is similar to the models of liquid to the treat them in a just like the spaces. So there is a different field of study for liquids, but for in these molecule crystal and in the amorphous solid crystals. So it's a big molecules. For example, these are the fluorines behave. They all have together to make the van der Waal forces. There is some, I think, freedom to make a lot of defects and how the fluoridants are arranged. But even if not, each of the sides of this crystal has, I think, 60 molecules. So we're not going cannot study such a complicated things, because this liquid crystal is what you, I think, have in the LED screens. For the example, they are allocated molecules that are also arranged themselves in a chain. So I think there is a partial ordering. So they're located inside each chain, but then there is a periodic structure of the chain. Means, for example, so there is an order in one direction. So is the partially ordered system. So in the amorphous solids, there are a bit like a liquid, because the atoms are fixed here in this, and they have chaotic distributions in this figure of atoms. And therefore the distance between of the atoms, then is fascinating feats of study that we are can be studied from this from the amorphous this solid. So that was the about the amorphous solid. And here, because the spatial importance it has in the biology, and these are the structure that have made local order on the polymer. So this here is a repeated monomers that can be also can our be put it down onto the amorphous side. And here I think we can define the crystal, because there are something that can be described by a crystalline lattice. And we can also define the lattice in a very simple and mathematical way. The way a lattice that is a set of points which can be constructed as some, and that should be able to get one of these points to any other points by the combination of the primitive lattice vectors. So these are the just vector in 2D or 3D, and any point on the lattice can be described by this formula in this by this formula. So every point of lattice belongs to this family, and you can also reach any point of lattice by finding the proper coefficient, and one or two or three for the primitive lattice vector. So here is the I think example of the collection of polymers that is the lattice. So here is the E1, the eight-dimensional one, and here is the A2 primitive lattice, and A1 and A2. And we can also get to any point on this plane by going over by one and by VT a certain number of times. So this point I think first highlights here. Here, let me let me go on to the pointers. So so here is the, so we can be go do twice by this and by then this to reach this point. So by therefore that's why this point can be noticed with the square brackets to this like 2 and 1, 2 and 1 in the square brackets. So this is the regular shape of the various crystal to denote the that we're gonna be a planes on the lines that could be also cut through a bunch of points. So these kind of notations, I think, are the frequent in the crystallography are some. I think the silicon 111 are plain, or gallium arsenide are 0, 0, 0, 1 grown into the 0, 0, 1 direction, and that would be the referring to the crystal structure. So here was something about the lattice pattern of the primitives. Lateral vertex is not unique. So here we comes to the more example. The couple because we have some various lattice, as you know that this is the square arrangement of the 2D examples, but this is a hexagonal one. So for the hexagonal one, angle between 1A and A2 is 120. So between them, so that is called, it's a hexagonal lattice. So because check in this case, so we can also get any lattice of the combination of A1 and A2 at I think at 90 degree, and because it's a superior lattice, but so that's why it can be also get through by liking this one, by and liking this one. So it's up to the this so that's why 1 and 1 could be adding up. So here are the lattice is a collection of points, and it is defined by the primitive like lattice vectors. So we will actually reserve the words for something else. So it's a primitive lattice, and this choice is not unique. So we can also choose a various combination from this pattern of the lattice vector, because these are the six years of the primitive lectures. So we can also get any point between the lattice by the combination of this one. So some of these it's more obvious than for the others, but for the example, if we look at the lower, if we look at the lower at this side, it looks like it skips at a lot of this age. So it's a very far, but I think we could get the examples more I think at this point, at at this point. Sorry, here at this point. So and this kind of vectors by using draw this one. So these are the combination liner of the vectors that we can also get to any on this lattice. So the choice is not unique. So however, to be a primitive lattice vector, we need to be give any point of lattice on the basis, and some are more of the more convenient, but I think we most probably not want to use these, because you can might want to use these two certain situations from the here. So here was something about the crystal. So here in this slide, so sorry again for the pointer options. So it is a very important slide. So because it's a cell of lattice, right? So we can also call a unit cell, because when cover the entire space, we can little bit know in the product way. You can also tar the entire spaces by reproducing this region space. That's why we call it the unit cell. So for in the picture here, in this picture, we can easily get that keep on repeating this green shape, this shape, without add any gaps, left or right. This plane up to the unit cell. So we can also completely fill or the tile of spaces uh, bear means such a reconstruction of the spaces of the lattice. So this kind of unit cell is, I think, already familiar to form a 1D chain. So I think there we have a lattice contents that we can also use to repeat one dimension. So I think primitive unit cell for a periodic crystal is a unit cell containing exactly one lattice point, and it is something sometimes more convenient to use a unit cell because that is not primitive. So we often refer to this as a conventional unit cell for that lattice point, for that lattice type. So on the other way to construct a primitive unit cell, it is to determine the Wegener status unit cell. So into the graviton lattice and all the points that are closer to that point to any others. So into very important the frame itself that are exactly on the lattice point, right? So we could also include 10 lattice points in many times to cover the entire space by unit cell by primitive cell is when only a point like is shown in this picture. So then by the repeating the unit cell, so we could be able to cover the entire space using the primitive lattice vector. So uh, in this so we can also sometimes use conventional unit cell. We can also a conventional unit cell for the lattice type that is from derived from the convenient. So it was called also the unit convenience unit cell because something that it makes our calculation inconvenient to see the inner working of lattice, but may I think include several of the points of a lattice right in that case because it not be a primitive unit cell and a conventional unit cell. So for a sample lattice, it is fairly, I think, easy to identify a unit cell. Like if we look into this picture, just we can also draw some shape around the one point from the right side of the of this shape. we can also enter the planes for more complicated lattice. So I think it's a very easy algorithm for finding a primitive unit cell, which is called the Wegener cities unit cell. So this one. So there is, I think, a way to identify a primitive unit cell for any lattice. So I think so we need to go further in this slide. So it's I think much like a primitive lattice vectors because it's not unique. We can also see from this picture that this is not a unique primitive in the particular I recently described in the previous picture in the previous slides. So around these lattice point and one of the illustrate of the boundaries of the primitives unit cell, and that we can be also deserve depending on the purpose, perhaps our I think ability to arrive these boundaries. I could be, I think any of these fit in the definitions in the picture, because by translations by the primitive the unit cell, we can also tile the entire space regardless it's a look like so this is, I think, all the primitive cell that could be also not unique. So no, we go to the next slide. So here are the next slide. So we have a grain shape in this slide. We have if we look this shape, if we talk about this is in this area. So I think it's a point in the lattice. So what I did, I just I think would shift a bit, and I placed in such a way the lattice points are in the corners, and this is, I think, actually a valid primitive unit cell. So, but it introduced another interesting concept of sharing lattice points between several of these unit cells. So, in fact, we can say that in this case, that is each of the point contributes one fourth of a point to this unit cell. So the total number is 1 point, but we can take the split into the four pieces, but they add up into the one pieces. So from this so from this pieces, we can figure out the direction point is in this directions. Here you can also see, because it's a four quadrants. It's a four quadrants of the single point of the sublet, and one points belong to the four different unit cells. So in this case, it's case 1/4 of a point to count the number of point cell per cell a few times today in this science, in this condensed matter physics and condensed matter physics codes. So I think they are all add up to the lattice point in this area, and I think it's a large angle that can and contribute less of the points So many cells, I think, one that is belongs to and just the fraction of a point. So it contributes the lot of primitive cell. So here was all about this slide. So I think we'll need to go to this the next slide. So here I think it's a good primitive cell, and we have in this case we have one half of a point here and one of a point here. So total is a one. So total will be the one, and so we call that's why we call it the coordination number. So uh, so here in this slide. So uh, in this slide. So we talk about the primitives operation, calculate the number here. We if we get the one, so we can get the one. Sorry, sorry, I think due to the using of pointer, so maybe I'm not able to write down the clear because it's like a whiteboard, so that's why sorry for this. So uh so 1 and plus 4. So it would be the triangulated space, and it's not a primitive unit cell because it has to include the lattice point, maybe split between the four. So but the coordination number, so one is conventional unit cell, because our analysis is with an orthogonal set of a primitive lattice vector. So in this case, this would be a conventional letters. So okay, we need to run the slide. Sorry. So yeah. So here is the next slide. So I think from this slide, a primitive a unit cell for a complicated lattice, we can also might get the other ones. Here is the lattice that has these kind of points. Here in this point, here we have some points. So in this we have some points here in this slide. So atom, what we can be do in this the corners that I have did and noted down. So its nearest neighbor atoms to the one half distance between these two, and the atom that we choose is to the nearby from here. And I think at the half distance we can also draw a line perpendicular like this one to to the corner of this one. So here I think uh, here I think we can also find the shape that be quite not trivial for the red dashed shaped in this picture. I think we can also do the three-dimensional, but it would be complicated, obviously. In three-dimensional, it would be a unit cell. So the atoms of the half distance and do this procedure. So we can also see in this picture. So we have in from here this point. So it's outside of the red shape. So it's formed by the closer atoms. So we don't further away from this point. So any from the animal species. So the so these what would be the statements that I think when we finding half these distance and making a normal lines to them and connecting them into the shapes, we can also cover the space 2D or maybe the 3D space, or because these are called the Wigner sites perimeter site. So the smallest volume enclosed in this, so in all the spaces from this figure. So because sometimes it's a very complicated. So so I think from the Wigner site's primitive cell, sorry, from the unit cell, so we can also get through it. So now we need to go to the further slides. So here, I think we could be able to draw more about the show more about the Wigner site construction. So, for example, for this lattice that we uh, 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 placed here in this figure, the Wigner Satis constructions is looks like these shapes, these shapes, and drawn a few of them can also see the entire space that can increase by the kind of shapes. So I think this is a valid unit cell, and it is a primitive unit cell because each one includes one data pointers by its but it's so we can also put it the one into the middle and one into the half distance and to only to the lattice points around it. So for such as this Wigner Satis constructions, it's a bit complicated because it's a slightly more complicated arrangement of atoms in it become the more complex. So I think no, we need to move further. So here is the next slide. So the primitive units lattice vector is some sub exceptions, I think, from the crystal and from the unit cell. So it's I think a variety of these lattice that could be, I think, are overlapping to this to the subset or an orthogonal uh, crystal only by the basis. So from this crystal, it's I think it's a complicated means. Like for example, we have different atoms in the same crystal, like sodium chloride, or has two different atoms and that means that the uh, if we go as sodium atoms to chlorine atoms, so we can change the type of atom. So those points should not be equivalent or don't to be equivalent. So I think therefore we have to expand the concept of a lattice, and it's a very important. So I think it doesn't mean in the solid. So it means that we need to go for one atom to the same atom in the cover periodically the entire lattice. So I think if we have several atoms, then we can also found a lattice with a basis, with a basic. What is means what by what I means that we can do a certain atoms like this one, and from around these atoms there are four different atoms, and there are smaller in this case, and if are smaller larger, it doesn't matter, but the distance away from this atom, and because it's the crystal structure of this material. So what we are going to define unit cell in the dash line. So in this picture, in the left picture, unit cell that we can large atoms for the smaller atoms. So, but I think this would be a unit cell, but we can cover the entire space. But with uh, to the lattice point, the corner of the unit cell, the black in this figure in this black dot. So from this direction. So I think these kind of primitive unit vectors that can be reproduce the entire space of these points. But I think the little points correspond to any in between the atoms, right? And all the atoms in the inside of this unit cell. So I think it's also a good description of crystal. So, but I think we need to specify a basis, and how we can specify. We just here is our unicell is dimensional is A, and it's in the lattice point here. This is one is 0 0, and now inside we have five different atoms here, and they are located at the position over a over four uh, a over 4, and 3 over and 3 over a, and sorry, 3 over a, and over 4, and 4 over a over 4. So with respect to the positions and unit cell size. So then that lattice can also surprised by these positions. Here we can you can see from this picture. So it's also, I think, comes with the basis of this positions. So because those points inside the crystal, and so the position of the large gray, we can also do the extra points inside the unit cell, but I think it's not a basis of the basis vector like our icons of eigenfunctions in the quantum mechanics. So this basis means that this inside unit cell there is an additional atom. So we have to more complicated this basis in two-dimensional lattice. So it was just for example. So in in this uh, in this in this basis, it's because simply describe periodic arrangements in these figures, in these above figures. So I think each region can be found out from the large gray atoms and sorry for using the pen, and small dot gray atoms here. So in the repeating periodically lattice point from the above figures. So uh, the positions are here, so we can also find from this picture. So here was something about the unit cell of the basis and the positions at different atoms. So I think we need to move further. So in this unit cell, the I think there is are five atoms applied to this lattice because it's the same lattice as we looked into the previous slides. But I think it's colored, the atoms with different colors, with the different atoms of different materials. So they are not equivalent anymore. But if I start with this atom, blue atom, so and then we go to the red atoms, I think we have to skip one horizontal direction in this side. So in my in primitive lattice vector A1 and A2, we can skip one on atoms. So a unit cell include one red and one blue, and and in the primitive lattice vector is often taken. So, but I think in the primitive unit cell, it has several atoms, right? Each, and we have to one lattice site, but only means that atoms can be a primitive cell with uh, several atoms around this. So, for example, uh, if we know the largest constituent atoms, I think it would be convenient, but it does not go for one to another atoms because sometimes it skips to the situations. So this case we have some basis for the some lattice red atoms at 0 0 direction, and this one as 1 over 2 and 0 directions because it's 1 and a half at 0 direction. So we can reproduce the entire basis of the blue atoms about these. So in this I think it's also a good cell, a union cell, and it's the same story behind this because we have two atoms per unit cell. So then we can also make sure that this is the case, because this unit cell from here is the contribution 1 4, sorry again, 1 4, and this one half, and this one is 1/2, and from this. So here we can also see the only one lattice point, only one lattice point from this figure. But I think just the red the points, because it's a half. So that's why we can also see. So now we go to the next slide. So the red, it's about, I think, about the uh, 2D, but I think it's a little tedious. But I think it's nice to has a lot of nice geometry in these pictures. I think it's a most 3D sample cubic lattice. So I think atoms are in the vertex of cubes. So we can see from this picture, from a simple cubic, where all the distance are atoms between the adjacent, it's already cubic here. If we imagine the atoms and balls, they will be, I think, stacked. So I think it's sitting up with each other, and the size of each one interbound is in the radius of this ball one. I think right, yeah, from this ball, I think the such a lattice from this picture from here. So we can also guess that why it is the half of the unit cell, that from the lattice points in each of the unit cell. So we look at one atoms from in this picture, and it's belongs to the some some lattice area. And here in this picture, so here are some 1/8 of atoms of the total. So each of eight of them belong to the eight, and there are eight of them, uh, 1/8 time here, 1/8 in this slide. So I think number of atoms per unit cell in this slide. So if we take the total numbers of the unit cell, we will get the more, uh, we can also get the same calculations from this unit cell. So here is the example of real material. So because I'm just talking about the overview of the crystal structure, so that's why I would like to take this picture. I think this is the material, that is the cubic lattice, uh, but the atom is not, I think, arranged, because the atoms in one is in the middle is different varieties from the other of the corners of the cesium, of the of this mid because the proper description of this is a cubic lattice, but I think it has a basis, and in this basis it's have two atoms, and cesium have 0 0 and 0, and chlorine at one half, one half, one half. So chlorine in one in the middle, one in the center of each of the cube. So it's looks like a more cesium than the chlorine, because it's because cesium are shared between eight different unit cells. So actually there is one cesium per unit cell, and there is one chlorine ratio of them, exactly one by one by the combinations. So here was something about the previous lecture. So because the time is very short, so I need to move further. So here in this slide, so uh, I'm just talking about now to give the view of the by a showing the examples. So in this figure, so the corner of the coloring completely reserved in the corners, from the hairs in from the corners, from the center, from the like this one. So is this picture is, I think, quite where the lattice of cesium atoms, the chlorine atoms, is exactly the same crystal. So it's good. It means that this one is particular to interlocking simple cubic. So it's a simple cubic lattice with atom just on the cubes, and then shifted by one half in three-dimensional, uh, one more cubic lattice of the green balls, these in this picture. So here was something about the this. So here is the another unit self of the body center cubic lattice, BCC. So let us point and from here, so from from this conventional unit cell, I think the lattice points from the one the, this middle is the one half of the cutting. So it's a eighth time, I think. Eighth time, I think. Sorry, yeah, half and eight, one half and eight times to the crystal structure of this material. So if we draw this lattice into the unit cell, so I think two lattice points per unit. Sorry, here is the eight. So here is the eight. Sorry. So then we can do the four, two. So it's a more frequently occurring situation with the convenient unit cell, because it's a single atoms compound from the lattice, and and this is short of conventional convenient way of the plotting the lattices by looking from the top here to the labels. So here are some also plan view of the enabled lattice point at height 100 at a over 2 from the top. So from this means from like this way, sorry, from like this way. So you can encounter this kind of notations that would be obviously 2 points here because it's a labels with one to reproduce this entire picture. So here was something about uh, the the plan view, and it's you can also see the more efficient sphere of the unit body soon cube lattice. So we move to the next. So here is the BCC lattice of the environment, that the initial motivation for you to believe that all these atoms are on the body center qubit or the part of the same lattice. So even if not simple arrangement of these atoms, it's interesting. So here was something about the crystal about the BCC lattice. So here we need to talk about the uh, 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 simple cubic with basis and cesium and chloride versus uh, with basis and from the simple basis and with the cubic, and it's a revealed. So it will be a simple lattice with the basis because two atoms, this one and this one, is a simple cubic with the simple sequence because CS at 0001 and CS at one half and half. So it's a because due it's a central atoms is described at this body centered. So now we need to go to the next slide. So it's the shape of quite a complex uh, so of the Wigner Citus primitive of the unit cell for BCC. I think these are hexagons to the connecting by this, but you can shape this unlike this one from here to the next atoms of the next cube. So I think this is the kind of shape that we are going to get from the application because this is very useful. But this is a true primitive unit cell containing just one lattice point by definition, and this is looks for this lattice is a kind of motivates that why we often this one uh, which is not primitive by the center onto the two lattice sites as per conventional convenient one lattice. So here was something about my presentation. So thank you very much for listening. So at the end, I just would like to thank you to Professor Dr. Hong Wanmin for providing this great opportunity to understanding the basic concept of crystal structure. So thank you very much for listening.